Hi, my name is Divim Kataria. I'm a tutor at the Engineering Tutoring Center, and today I'll be hosting the Math 243 study review. Our agenda for today, the topics we'll be covering is big O notation, number basis and converting them, modular arithmetic, mathematical induction, and we'll be discussing a few tips and tricks and some things that you should keep in mind while doing the exam. What's big O notation? The big bounds. So the big O is represented as O of G, where G is any function. This is always the upper bound value of a function, and F grows no faster than G. And it signifies worst case scenarios since it's always the highest O value. Now, big omega, this is the lower bound. This always represents the best case scenario, and F grows at least as fast in G in these cases. We'll see them worked out in the examples that we'll be covering right after this. And then big theta, this is called as a tight bond. And in here, the function f and g grow at the same rate. This is both O and omega. So, agenda for today. We have already discussed that. Now, properties of big O and the order of growth. So, how do we want to calculate big O? So, there is two rules that we'll be using. The first one is the sum rule. If we add OM and ON, the resultant O will be O max MN. So, it'll just be the maximum number out of M and N. And the product rule, we just multiply the values of M and N when we want to calculate the product of two different functions with different omega values. Now, there is a general order of growth that we follow, which we can see over here in the graph, or in the diagram on the bottom right, and also the statement. So, one is the least big O, and it keeps on growing up to log n log n squared, n cubed to the power n, and then n factorial. N factorial is the worst time complexity of big O there is. Now, review questions for big O. If If fx is ox cubed and gx is ox to the power 4, what is the lowest big O estimate guaranteed for fx multiplied by gx? So, when you see these two, let's multiply the x values because as you remember in the product rule, we discussed when we need to find the product of two functions, we do OM multiplied by ON. What's our m and n values? Our m values x cubed, our n values x to the power 4. So O m multiplied by n will be O x cubed multiplied by x to the power 4, which will be O x to the power 7. So the lowest big O estimate guaranteed for fx multiplied by gx will be O x to the power 7.
Can I ask a question real quick?
I'll be detailing all the questions at the end of the review. That's fine.
Well, I just want to know if I should stay or not. We're on exam 2 and we're not going over this. So is this just for another exam?
Yeah.
This isn't for exam 2?
This for exam 3.
Oh, okay. Yeah, we're not on that lesson yet. So I'm actually going to leave the chat. You're on a lesson
Okay.
we're not. We haven't started yet.
Okay.
Okay.
Give me 1 minute, guys. Okay, so let's continue. Now, let's see. So the product rule over here This is basically what we did with the annotations, but over here we can see it implemented. Technically, any value greater or equal to 7 will be the big O estimate, but since we want the lowest value, it would be 7. We can also say it is O x to the power 12, but we'll also consider this as O x to the power 7 because that's the less value, that's the most tight bound value, the lowest value that we can get. But any values greater than that would also be um, usable. Now, let's see if fx equal to x cubed and gx equal to ox to the power 4, what is the lowest big O estimate for fx plus gx? So over here, we simply want the highest out of the O fx values and the gx values. The highest value is x to the power 4. So our big O estimate will be x to the power 4 or just 4. Now, is it true or false? X cubed is O to the power O3 to the power x. Now, if you remember from the order of growth, we can see over here x cubed lies somewhere over here and 3 to the power x will lie somewhere over here. Since 3 to the power x is has a higher growth order, we can say yes, this is true. Since whatever the higher value is, we can consider them. Now, is 5x square equal to ox squared? Yes, it is because we do not really care about constants when we talk about big O. So yes, this will be true. Now we have to find the best OGX for fx equals 3x squared plus x log x squared plus x squared log x squared and this entire equation. So how do we want to go about this? We want to separate all of these and find the O of x individually, and then we'll go on about them. So for this one, what is the highest OX? It will be x squared log x squared. Why is that? X squared log of x squared can be rewritten as the 2 goes forward. So 2x squared log x. Now, you see, this has the highest x component, and this also has log x. This has log x squared, but so when the 2 comes forward, it'll just be 2x, not x squared. So this has the highest x component. That's why for this particular equation, our O x will be On will be x squared log x. Now moving on to this part, using similar logic, On will be x cubed, and for this part, it will be x to the power 4 log x. So since this is technically in product, we'll use the product rule that we had initially used when multiplying time complexities. So the time complexity for this combined would be this was x squared log x, this was x cubed. The product for these is x to the power 5 log x. Now for this last equation, it was anyways x to the power 4 log x. Now, if you compare this with this, you'll see that this is a higher value and thus has a higher complexity or a higher big order of growth. So we want to find we want to use the biggest one to find the best O of gx. Thus, we'll use this. So the biggest one would be O x to the power 5 log x. Now, let's say it worked out in formal language. So we pick the highest n for this equation. We did the exact same thing as we discussed. Now, let's find the lowest integer case so that 1 to the power 5 is to the power 5, so on to n to the power 5 is O n k. Now, our highest element is n to the power 5. Now, this element has been repeated, let's say, n times. So the total number of integers would be n multiplied by n to the power 5, right? So how can we simplify this? N multiplied by n to the power 5 becomes n to the power 6. Now we need the highest O value for this entire equation for getting the best O n. So our O n would be O n to the power 6. We have to compare it to O n to the power k. And from here we can conclude k equals 6. Since there's n terms, this can translate as n multiplied by n to the power 5. This is equivalent to n to the power 6. Thus, lowest integer k would be 6 to recap. Now, let's move towards omega. So, which of these is omega x squared? So, let's see these worked out. The evaluating functions. So, fx equals log x to the power x. That's our part A. We can simplify this as x log x. Now, there is a short and neat trick that we generally like to use. If our so let's take this as n and our function, whatever we're taking that as m. If m over n goes to infinity, it is in the form omega. Now this is basically called the limit trick for omega. You want to plug x goes to infinity for this one. And as you can see over here, this is basically x log x over x squared. This becomes log x over x. Since x is a greater value than log x, it just goes to 0. So that's why it's not in omega format. Now, part 2, part B, x cubed over 2 plus x squared. So we don't want to divide x squared by x over 2 plus 1. So it becomes infinity. Thus, it is in the format omega. So we can see this worked out over here as well. X cubed over 2 plus x squared over x squared, which was our m term. Now this cancels out, this becomes 1. This cancels out, and this stays as x. So x over 2 plus 1, which is just infinity. That's why it's omega x squared. Now for C part, so this basically behaves like x multiplied by x in a way, which is just x squared for large numbers. And the ratio x squared over x squared is 1. Therefore, the part C is also valid and it is omega x squared. Now, for part D, x to the power 4 plus 2x plus 3 over x squared minus 2. The dominant terms in this are x to the power 4 and x squared. This ratio is basically uh, x4 over x2. The ratio is basically going to be x squared. Now, since we are dividing this with x squared using our test, it's basically equal to 1, and the result is therefore omega x squared. Now, for part E, x squared log x, we have x squared log x over x squared. This goes to infinity, and therefore it satisfies the omega x squared condition. So whenever it goes to in any number except 0, it's going to satisfy our condition, and it's going to be omega of x squared. Similarly, for the last part, we have 2 to the power x plus x squared. This becomes 1 when we divide it by x squared, and this uh, we can see that 2 to the power x has a higher growth order in comparison to x squared, so we can just say that this goes to infinity. Therefore, the result will be omega x squared. So, which of these are theta x squared? So, this is going to be somewhat similar, but we will have more conditions that we'll have to take into place. So, this has to always reach the ratio 1. So as you can see for this one, log x to the power x becomes x log x, and ultimately a remainder of log x over x is left after simplification with the ratio test. X outpaces the log x since has a greater growth order, and it's technically 1 over infinity, which is a 0. That's why the theta condition is not met. Now for this one, uh, same option as the previous one. We'll get x cubed over 2 plus x squared over x squared. This cancels out. We're left with x over 2. Now x goes to infinity. Therefore, we can say this technically outpaces the x squared. Therefore, it's not in theta format. Now, for the next one, this is roughly x squared. And with the ratio test, this is going to be x squared over x squared, which is 1. Our theta is met. That's why it's theta x squared. Similarly, for the next one, the ratio between these two terms is the highest terms here is x to the power 4 and x to the power 2, x4. Yes, this is mat 243. X to the power 4 over x squared. So the ratio simply becomes x squared. Now we have a term m over here. It just becomes x squared over x squared using the ratio test and becomes 1. It behaves exactly like x squared, and thus our result will be theta x squared. Now we have x squared log x. So again, we'll use the ratio test. We need the ratio to be 1 precisely for the theta condition to be met. Now we'll have x squared log x over x squared. We're left with log x over 1. Now log x outpaces the 1, of course, and it becomes infinity. That's why our theta condition is not met in E. Similarly, for part F, we have 2 to the power x plus x squared. Now, again, for the ratio test, we'll put it over x squared. This cancels out. We're left with 2 to the power x over x squared. Now, 2 to the power x has a higher growth order, so it will outpace the x squared and will become infinity. That's why the condition for theta is not being met in F either. So our conditions are only being met in C and D. Now, number bases and conversions. This is the next part. So we have hex to binary. Each hex digit is individually converted to a 4-digit binary value. Binary to octals. We start from the right side, group 3 digits, and convert them to an octal digit. Number of binary digits in hex. Number of hex digits multiplied by 4. Number of digits of n in base B. We use a formula. So we use floor log bn, and then we add 1 to that. Now, let's review some questions for that. So we want to convert hexadecimal 5A to binary. So we'll take 5 separately and we'll take A separately and treat these as two separate values. So 5 is basically 0, 1, 0, 1. A is basically 1, 0, 1, 0. We'll just concatenate them, and that will be our fully converted hexadecimal to binary 0, 1, 0, 1, 1, 0, 1, 0. Now, for octal, we group 3 and then we convert it to the form 8. So 1, 1, 0, 1, 1, 0, 0, 1. So over here, we'll group 3, these three, these three. Now you see there is no 3 digits at the end. We only have 2 digits over here. So just add a 0 in the front. Since it doesn't matter, we can just add a 0 in the front without it actually affecting the value for equation. So 0, 1, 1, 0, 1, 1. Now, as you can see, this is 1. This is 3 and this is 3. So final answer will be 3, 3, 1. Now, a positive integer has 100 x digits with leading digit a. How many binary digits will it have? Now, if we remember it correctly in one of the previous questions over here, how we converted from hexadecimal to binary was we separated these two digits and we grouped them in four. In octal, we group them in three. Over here, we group them into like we convert one digit into four digits. So we can say that one hex digit is basically four binary digits. So how many is 100 hex digits with leading digit A? It will be 100 multiplied by 4, which is 400 binary digits in total. Now, is it true or false? In duodecimal, which is basically base 12, A7B multiplied by 100 equals A7B 100. Now, what happens is in base 12, the written number as 100 actually represents 12 squared. So this number is basically 12 squared. Now, how do we know that? So 12 squared, 1 multiplied by 12 squared plus 0 multiplied by 12 to the power 1 plus 0 multiplied by 12 to the power 0. So this is 0, this is 12 squared. So which is 144. And it's a standard rule for these things that whenever we are multiplying the base with its square, we just append two zeros at the end. So we have A7B over here already, and 100, as we can see, it's basically 12 squared, and a base is also 12. It just become A7B double zero. Now, dividing hex FA3BC by 10, hex gives quotient FA3B and remainder C. Now, over here, we can see that 10 in hex is basically 16. How do we know that? 16, 1 multiplied by 16 to the power 1 plus 0 multiplied by 16 to the power 0. So 16 plus 0, which is just 16. So this would mean that since 16 ends over here, the last digit is going to be a remainder because that is too small for it. So our remainder is therefore C, and our question would be the rest of this equation, rest of the number, which is F A 3B. Now, how many digits does 3 to the power 8, 2, 3, 4, 7 have in base 3? So we'll use the formula that we discussed over here, log Bn plus 1, and we'll just plug it into that. So log to the base 3, since our base is 3, and our number is 3 to the power 8, 2, 3, 4, 7. Now, because of the properties of logs, whenever we have the same base and the same number starting over here, we can just cancel these out. And most importantly, before we do that, 8, 2, 3, 4, 7 is in the power in log, we'll just jump forward. 8, 2, 3, 4, 7. Then we have plus 1 over here, it becomes 8, 2, 3, 4, 8. So we have 82,348 digits. Now, let's move on to modular arithmetic. Now, what are the basic symbols of modular arithmetic? What are the different types of things we use? So there is this thing called as div, which basically asks us for a question. So it will basically be something like 14 div 2. Now, if you divide 14 by 2, it's just asking you what the question is. Now, 14 divided by 2, that's 7. Our question is 7. 15 div. Let's say we have a number that is not exactly divisible. So let's say instead of 3, let's write 4 over there. So we'll write the number that, so the closest number that's divisible to 15 is 12 if we do not want to have a negative remainder, which we never do. It's 12. So the quotient over here will be 3. Now, mod, it basically asks for remainder, and the one rule of mod is it can never ever be negative. So 14, oops, mod 2. There is no remainder left when we divide 14 by 2. So our 14 mod 2 is just going to be 0. Now let's say again we write the example of 15 mod 4. So what is the general remainder that is left when we divide 15 by 4? The closest number divisible is 12. Since we never want mod to be negative, we won't consider 16. So the closest number is 12. And what's 15 minus 12? It's 3. So our 15 mod 4 will be equivalent to 3. Now, A mod M plus B mod M is A plus B mod M. So all we do, if they have the same mod M, so the same mod, we'll just put them in the numbers before the mod, we'll put them in parentheses, we'll throw them in parentheses, and just add them up normally and multiply them up normally. Now, what is the GCD equilibrium algorithm, greatest common divisor equilibrium algorithm? We divide, we take the remainders, and then we repeat until we get the answer as 0. We'll see it worked out in the next couple of questions. So let's start with the basic one. Let's evaluate this entire equation. So let's separate this out. What is the answer for negative 14 mod 4? So again, we never want the answer for this to be negative. So we want to take the highest possible value. So highest possible value, that's negative 12. The remainder over here comes out to be positive 2. So this is equals to positive 2. Now 76 divided by 5. So 76 is not exact the exact fact multiple of 5, but what we'll do, we'll find the closest multiple of 5, which is what, 75. So 5, 7, so that's the question for this will be 15. We can see it over here. Uh, So this will just be equal to 50. So we do not care of the remainder over here. We just want to find the question, whatever the question is. So this equals 2, this equals 15. So now this is in parentheses. So what's 2 plus 15? 2 plus 15 is 17. Now 17 mod 3. Now, what is the closest multiple of 3 next to 17? Since you want always a positive remainder, we're going to elect 15. So 15 divided by 3, that is 5. Oh, sorry, it's mod. So we want the remainder. So again, we have to take 15. Now 17 minus 15, that's just 2. So our answer is going to be 2. Here we can see it worked out again. Now the next one. We'll use equilibrium algorithm to find the GCD. So what was the Euclidean algorithm? We divide, we take the remainders, and we repeat that until our answer is 0. Now let's see it worked out. So 1002 can be written as 1 multiplied by 999 plus 3, right? So next we'll pick this and formulate that. This can be written as 333 multiplied by 3 plus 0. Now we can see the remainder over here comes out to be 0. And whenever the remainder comes out to be 0, we stop our algorithm right there and then. The last non-zero remainder will be our GCD. So what's the last non-zero remainder? It's 3. So our GCD is going to be 3. Now, let's find the greatest common divisor for these. Now, we do not really need to use the Euclidean algorithm for this. We'll do it on a comparative basis instead. So, if we look at these two numbers, what's the common numbers in this? 5 and 7. We can eliminate 3 because 3 does not exist over here. So, 3 wouldn't be a part of the greatest common divisor that we get. Now, what's the highest power of 5? Or in 5 squared, 7 to the power 5. It's 5 squared. And what's the highest power of 5 and 3 multiplied by 5 multiplied by 7 to the power 9? It's just 5 to the power 1. We'll take the lowest possible value out of all of these, which is just 5, and we'll write it down. Now we'll do the same for 7. We have 7 to the power 5 in the first number and 7 to the power 9 in the next number. So what is the lowest possible value of 7? It's 7 to the power 5. So a greatest common divisor will be an accumulation of both of these individual values. It will be 5 multiplied by 7 to the power 5. So now we have this worked out over here. 5 multiplied by 7 to the power 5, which is a final answer. So now let's evaluate 12 to the power 1024 mod 11. Now, how do we want to work this out? We just want to consider the 12 and we have to see what's just 12 mod 11. 12 mod 11 is just 12 minus 11, which is 1. Now, after you get this one, we'll do 1 to the power, since it's 12 is to the power 1024, it's going to keep on, this remainder is going to keep on increasing in value. But since it's 1, it really does not, because anything to the power 1 is still 1. Mod 11, it's just 1. 12. So, next question. So, we have 23, 1, 2, 4, 5 multiplied by 21, 6, 7, 9, 1, 1 mod 11. Now, this is the implementation of the product rule property that we studied initially over here. So, let's calculate this individually. 23, 1, 2, 4, 5 mod 11. The closest number to this is 22, 23, just 20. We'll forget the exponent and just consider it on the 23 mod 11. The closest power to the number to this, that's multiple of 11, is 22. So 23 minus 22, which is just 1. We'll do the same for 21. So the closest number to this that gives a positive remainder, it's 11. So it becomes 10. So 1 multiplied by 10, which is 10, will be the answer for this question. We will just ignore the exponents. So the product of two numbers is 48, and the greatest common divisor is 2. We need to find their LCM. So there is a particular formula that some people use, and it's the product of two numbers. So let's say the numbers are A and B. So we can write this in the format A multiplied by B divided by the greatest common divisor of A and B. So this technically becomes 48 divided by 2 is 24, which will be our LCM. Now we need to find an integer n so that n mod 31 equals 9 and negative 31 is less than n, which is less than equal to 0. So what is the general formula for this? So n mod 31 is 9. We can technically reframe this as n equals 31 times m plus 9, where m is some random integer which we are multiplying with 31 and then adding the remainder n to it. So m is basically the question over here to get the value of n. Now we had negative 31 less than n, which is less than equal to 0. So negative 31 less than equal to, so sorry, just less than 31 m plus 9, which is less than equal to 0. So let's start simplifying this. So we'll first get rid of the 9. So we'll subtract 9 both sides. We get negative 40 is less than 31m. It's less than equal to negative 9. So I'm just going to mark this equation and rewrite it. So now we want to get rid of the 31 over here. We just want the value of m. So negative 40 divided by 31 less than m is less than equal to negative 9 over 31. So let's find the value for this. Negative 40 divided by 31 is negative 1.29 less than equal to, it's negative 0.29. Now we can see that we need to find an integer n, right? The only integer possible between these two values is the integer negative 1. So we'll use m as negative 1 and calculate for n. So n equals 31 m plus 9. M is negative 1. We'll just plug this in. Negative 31 plus 9, which becomes negative 22. And that's the value of n. Now, one of the last parts, but one of the most important parts is mathematical induction. Now, there is a basic template that we will follow. We'll state exactly what we are trying to prove. We'll verify the base case. We'll write down the inductive hypothesis involved. We'll write the inductive step, and then we'll write the concluding statement. So we need to prove 8 to the power n minus 1 is a multiple of 7 for all values of n greater than or equal to 0. So how will we go about this? What's our base case? Our base case is at n is greater than equal to 0. Let's see if this is valid for our base case. So I'll write this as BC for now. 8 to the power 0 minus 1. So 8 to the power 0 is just 1, which equals 0. 1 minus 1 is just 0. So is 0 multiple of 7? Yes, it is a multiple of 7. So our base case is satisfied. We need to write these statements too. Then inductive hypothesis is we'll assume 8n minus 1 is a multiple of 7 or some value of n greater than equal to 0. Now, after that, we'll perform our inductive step. So, in our inductive step, we have to show that 8 to the power n plus 1 minus 1 is also a multiple of 7. Now, how will we show that? So, 8 to the power n plus 1 minus 1 can be written as 8 to the power 8 multiplied by n minus 1. Now, we can add and subtract any number over here without it really affecting the equation, right? So we'll subtract 8 and then we'll also add it over here. Now, let's factorize this and this. So factor out the 8, 8 to the power n minus 1 minus 1 plus 8. It becomes 8, 8 to the power n minus 1 plus 7. So, because of assumption from the inductive hypothesis, we already know that this is a multiple of 7. So, from that, we can say that since this is a multiple of 7, any constant multiplied to a multiple of 7 will also be a multiple of 7, right? So, this will also be a multiple of 7. 8 multiplied by, let's say this is in the format 7c, 8 multiplied by 7c. This will be in the format 56c. Now, this is also a multiple of 7. As you can see, 56 is divisible by 7. Now, we're adding 7 to that on top of it. So, if we add 7 to a multiple of 7, it's still going to stay in the format it is a multiple of 7. And thus, over there, we can conclude that because our base case is true and the inductive step proves that every valid term guarantees the next term is also valid. So by mathematical induction, 8 to the power n minus 1 is strictly divisible by 7 for all values of n greater than or equal to 0. Now we can see this in a more formulated way in this text. So the base case, it's the same exact process. We just need to make sure that we write the statements properly because statements are the main marking factor for for the inductive hypothesis questions. So over here we proved our base case. We wrote an inductive hypothesis. We wrote an inductive step. This is the exact same format that we did. Just a little bit concise, and then the conclusory statement. Now let's move on to the next one. So for this one, we can see the base case. Let's verify the base case first. So if we just have n equals 1, which will be our base case, we'll just have the value 1 multiplied by 2. Now, over here, we'll have 1 multiplied by 2 multiplied by 3 divided by 3, which is also 2. So our LHS and RHS have the same values and our base case is satisfied. Now, inductive hypothesis. So let's assume that this is true for some arbitrary integer n greater than equal to 1. Now, we want to be more precise with wording over here. We don't want to say some n is greater than equal to 1. We want to say for some arbitrary integer n, which is greater than equal to 1. We want to be precise with the wording for inductive hypothesis. Now, let's do the inductive step. We must show sum to n plus 1 equals n plus 1, n plus 2, n plus 3 over 3. It should be equal in this format. So, sum to n plus 1 equals sum to n plus n plus 1 multiplied by n plus 2. So n multiplied by n plus 1 multiplied by n plus 2 divided by 3 plus n plus 1 multiplied by n plus 2 by the inductive hypothesis. Since we have concluded that since this is our assumption, we can just write it down over here. Now n plus 1 multiplied by n plus 2 multiplied by n over 3 plus 1. So after that, we do n plus 1 multiplied by n plus 2 multiplied by n plus 3 over 3. So this is just, we keep on simplifying and tweaking up our equation to prove that our base case and the inductive step, which is basically proving that inductive hypothesis is valid at an n plus 1 point, is correct. So over here, we can see that this is indeed in the format n multiplied by n plus 1 multiplied by n plus 2 over 3, since we're just adding 1 over here. So n plus 1, this becomes n plus 2, this becomes n plus 3. Now, in conclusion, because the base case is true and the inductive step proves that every valid sum guarantees the next sum is also valid. Now, by mathematical induction, the summation of formula is proven true for all values of n greater than or equal to 1. Now, what are the some common mistakes that we end up doing while doing inductive hypothesis? Incorrect wording. We assume Pn is true for all and no, we want to be very specific for this. For some arbitrary fixed n, for some arbitrary integer n, we want to be specific with our wording over here. Now we sometimes substitute n plus 1 without showing any work. Like I kind of skipped over that step in the last question. No, we want to be very specific. We want to show it that n plus 1 work exists, and I'm not skipping any steps. It should be thorough. The more thorough you are with proofs, the better it is for scoring. And just writing Pn plus 1 and saying proved is not a proof. We must derive it using the using all the hypothesis tests and the hypothesis work. Now, it's the starting base case at n equals 1 when n equals 0 works. So, sometimes in questions, we got to be careful while reading. It might say that the base case is going to be n greater than equal to 0, and we might just start working with n greater than equal to 1, or some lesser value might work out. We always want to start with the base case. If we use any value except the base case, that might mess up our question, might mess up our hypothesis, and it'll cause us to lose points. Now, sometimes we forget the plus one term. Now, when we're extending the sum, like we did in the last question, we write the sum to n. We forget to write the n plus one term explicitly, and we need to do that each and every time. So that's all for the study review. Uh, Good luck everyone for their exams. Now, if there is any questions, I can take them.
Yeah, real quick question. So for induction hypotenuse, what we were just doing, long story short, all we have to do is just